Welcome to the MERL CD-ROM. MERL is an interactive multimedia presentation that will teach you chemistry while telling a story of environmental technology development. This menu provides access to the major sections of MERL. Move the mouse over the red flags to see explanations of what material this section contains. Click on the Chapter 1 flag to begin. Chapter 1 provides background on the sources, fate, and effects of groundwater contamination. It is intended for those who are not already familiar with this aspect of environmental science. This page provides an outline to the contents of Chapter 1. The story follows the progression of the ovals in a clockwise direction. Move the mouse over an oval for more explanation of each topic, or click on an oval to advance to that topic. To continue Chapter 1, click on the right arrow in the toolbar below. The water cycle is one of the most fundamental concepts of environmental science. Note that it's a cycle, in that water is continually being recycled through the pathways shown. You can mouse over the colored dots to get more information on each process. Contaminants also travel through the environment in well-defined ways. This figure shows some of the major routes by which contaminants can be introduced into the environment. Note that many of these routes lead to contamination of groundwater. Not all contaminants are chemicals. For example, E. coli is a bacterium that is considered to be a contaminant when it occurs where it doesn't belong, such as in food or groundwater. However, our concern here is with chemical contaminants, of which there are two major types, inorganic and organic. Mouse over the thumbnails to get more information on the important inorganic contaminants. The environmental fate and effects of organic contaminants can be quite different than that of inorganic contaminants. Organics contain mostly carbon, hydrogen, and oxygen atoms. Many organic contaminants also contain chlorine atoms. Mouse over the thumbnails for more information on each of the major types of organic contaminants. Many organic contaminants have low solubility in water. Therefore, large amounts of the contaminant will form pools known as non-aqueous phase liquids, or NAPLs. NAPLs can be formed by gasoline and other petroleum hydrocarbons, as well as by chlorinated solvents like PCE and TCE. When NAPLs occur in the ground, they move in peculiar ways. These images are from a classic set of experiments done by the German hydrologist Schwille. They show a NAPL containing a fluorescent dye sinking down through a tank that is designed to simulate a cross-section of an aquifer. In addition to transport, there are chemical reactions that transform contaminants into other chemicals. These reactions may be fast or slow, and the products may be better or worse than the original contaminant. Some of the major transformation processes are shown in this figure. The impact of contaminants is assessed in terms of risk. the probability of negative impact due to the contaminant. Risk requires exposure to the contaminant and toxicity by the contaminant. The negative impacts that concern us may be to humans or to ecosystems. Click the Learn More button for more details on these two types of risk. The complex issues involved in assessing risk to human health are nicely illustrated by the story of chemical contamination in Woburn, Massachusetts, which has been popularized by the book and movie called The Civil Action. Note that chemical contamination can impact people by a variety of exposure routes. The issues involved in assessing ecological risk are also very complex, as is illustrated by this example involving unexpected consequences of pesticide use in Malaysia. The figure shows a web of impacts created by the use of insecticides. This page summarizes the major points presented in Chapter 1. Move the mouse over the blue rectangles of text for elaboration on each point and its relation to the other points made in the chapter. Chapter 2 provides background on the science and engineering of dealing with contaminated groundwater. It includes an introduction to iron walls, a promising new remediation technology consisting of permeable reactive barriers containing zero-valent iron. Sometimes, in the frames that follow, we will refer to permeable reactive barriers by the acronym PRBs. This page provides an outline of the contents of Chapter 2. The topics progress from the problem to discovery, development, and commercialization of iron metal for remediation of environmental contaminants. Click the right arrow to start at the beginning, or any of the blue ovals to jump to a particular topic. The options for treating groundwater have evolved over the years, as the priority contaminants have changed and as available technology has advanced. Initially, most groundwater remediation was achieved by pumping the contaminated water to the surface and then treating it above ground. We now consider this to be an inefficient and costly approach. Today, most technology development is focused on in situ means of remediation, such as permeable reactive barriers. Envirometal's animation of a permeable reactive barrier demonstrates the general concept. The contaminated groundwater flows through the PRB. The reactive material in the treatment zone degrades the contaminants, and then the treated water emerges down gradient. Critical to the success of permeable reactive barriers was the discovery that iron metal could be used to degrade some common groundwater contaminants. The discovery of iron metal as a means to remediate contaminated groundwater is a good example of serendipitous discovery in science. Serendipitous discovery is the discovery of one result while looking for another. The experiment that led to the discovery of iron as a reactive medium for groundwater remediation was actually designed to investigate another problem. The researchers set out to determine if the materials used to case monitoring wells could affect the concentrations of contaminants found in water samples. They found the effect they were looking for, but also found an effect that they were not expecting, which turned out to be much more interesting. Once a new idea for an approach to groundwater remediation has emerged, the inventor must then develop a proof of concept. The first step in the process is to demonstrate the desired chemistry in small bottles in a laboratory. This allows the researcher to evaluate all the important experimental variables. Remediation strategies that work well in laboratory bottles are then tested in laboratory columns, such as the one shown here. Column studies are better than experiments in bottles in that they can simulate hydrogeological conditions in the real world. If a technology performs well in the column tests, then it is ready to be demonstrated at the pilot scale. The pilot test facility shown here is part of the large experimental aquifer program at the Oregon Graduate Institute. Here, researchers use swimming pool-sized tanks as model aquifers, so they can simulate some of the complexities of the field, but still have much of the control of the laboratory. The first field test of an iron PRB took place at Base Borden in Ontario, Canada, performed by researchers from the University of Waterloo. This test was run for about 5 years, starting in 1992. The data collected provided valuable information on the performance and longevity of iron walls. The success of this demonstration convinced many people that iron walls might make a viable commercial remediation technology. The first full-scale commercial site to be remediated with an iron PRB was in Sunnyvale, California. The site was contaminated with perchloroethylene from previous circuit board manufacturing operations. The old above-ground treatment system was replaced with an in-ground iron wall. This allowed the owner to put the surface back to commercial use. Today, there are many field sites in place that have iron PRBs. Most are for treating chlorinated solvents, but some are for treating other organics, toxic metals, or other inorganics. A representative selection of early field sites is presented here. Most of the iron used for groundwater remediation is made with recycled waste from machining or manufacturing operations. This material is produced mainly for conditioning concrete, but some suppliers of granular scrap iron are beginning to develop materials that are optimized for use in iron PRBs. Some of the most important types of granular iron are shown here. The use of iron as a reducing agent for environmental contaminants was discovered and tested using chlorinated solvents. Since then, it has been shown that iron metal can degrade a variety of other contaminants. The list of treatable contaminants now includes many toxic metals, some inorganic contaminants like nitrate, explosives like TNT, and of course a wide range of chlorinated solvents. Most early installations of iron walls were done by placing sheet piles to isolate a box that was excavated and then backfilled with iron. The sheet piles were then removed, leaving behind the permeable reactive barrier. This technique gives us good control of the resulting wall configuration, but is relatively slow, and is limited to shallow walls. The horizontal trenching machine, which was originally developed to lay drain pipes, can be retrofitted to install permeable reactive barriers. It works by digging a trench with a large chain and simultaneously backfilling the trench with iron poured from a trencher box. This technique is very efficient at installing long, narrow walls.
The mandrel is made of 3 channel iron sections welded together with ironed end plates creating an I-beam shape. The opening at the top of the mandrel is the chute where the iron filings are loaded. A center rod extends from the top all the way to the end of the mandrel to facilitate shoe removal once the desired depth is achieved. The mandrel weighs 14,000 pounds and is over 70 feet long. A disposable shoe protects the opening during the probe driving step. The center rod seen is retracted during emplacement and pushes the shoe off pneumatically. The walls between the channel iron have cut-out sections to allow iron to flow to each of the chambers to equalize the distribution of iron in the probe. These cutouts extend for about 12 feet up into the mandrel. The rod is in a protective casing to minimize bowing. After assembly on site, the rig is moved into position over the wall. Fine-tuned positioning of the mandrel is possible, but difficult due to the size of the equipment. In addition to maintaining control of the X and Y coordinates, the rigging controls the yaw of the beam by means of rollers. This allows the mandrel to slide evenly up and down along the length of the blue and white guide rod. The sequence for probe emplacement begins with pounding the shoe into place. Next, the beam is lowered into position. The fins overlap the previous probe and help maintain a continuous wall. Once into position, the plumb is checked one last time with a 4-foot carpenter's level. Finally, the beam is vibrated into position using a 22-ton electric vibratory hammer. Each probe took between 6 and 10 minutes to drive under optimum conditions. A blue hopper transfers the iron from the shipping bags to the mandrel. From there, the iron was allowed to free fall into the chute and fill the hollow tubes created by the channel iron. One bag was loaded into the mandrel before the shoe was removed using a hand-activated hydraulic pump. Once both 1.5-ton bags of iron were in the mandrel, which filled it up to the bottom of the chute, the mandrel was vibrated out while testing the hollowness of the tubes. This was done by pounding on the external surface. The iron wall was filled to the surface to allow visual confirmation of wall continuity. The entire sequence for one probe, from start to finish, takes between 45 minutes and 1 hour. This process utilizes a guide beam that supports an injection nozzle. The nozzle houses high and low pressure ports used to cut the formation and fill the void with an iron slurry. The beam used in this process is a 36-inch I-beam with the corners cut from the leading edges of the flange to facilitate positioning in the guide box. A movable lateral plate provides control of the positioning during emplacement. The water jets are started at low pressure to reduce the risk of injury from high-pressure water above ground. Pressures up to 6,000 pounds per square inch gauge are used to force the water out at approximately 20 gallons per minute. Once the beam is into position, it is lowered into the guide box and the water jets are pressurized. The 7-ton vibratory hammer and the high-pressure engines are activated and the penetration begins. Complete cycle times are between 1 and 3 hours for each probe. During the drive, the plumb of the beam is checked several times with a 4-foot carpenter's level. Excess water and cuttings generated from the process are pumped off for analysis and final disposal. At the heart of slurry production is the mixing truck. As can be seen, here is where all the components come together. An enzyme is mixed with the hydrated guar to speed the breakdown process. The guar is in the large clear flexible hose. The enzyme breaker and binder are fed in a smaller tube, and the iron comes from the conveyor. The rate of travel for the conveyor belt and the pumping of liquids controls the consistency of the iron mix. This varied slightly during the demonstration, yielding different densities of the slurry to be injected. The result is a very viscous mixture. Densities up to 190 pounds per cubic foot were obtainable with this mix. This is compared to the dry bulk density of iron, which is 217 pounds per cubic foot.
This project introduces a new construction technique for installing a permeable treatment wall into subsurface soil and a rejuvenation technique for maintaining kinetic degradation capabilities of the wall for an extended period of time. The permeable treatment wall acts as a pumpless well where contaminated water flows into the treatment cell and comes out clean. In this test, the wall was put in place 40 feet below land surface, using a combination of deep soil mixing and vibro installation techniques. However, the combined technique allows for installation of considerably greater depth. The design for this project included 11 deep soil columns with 10 upgradient boreholes to ensure perpendicular flow through the treatment zone. It consists of deep soil mixing columns combined with a mixture of iron and gravel, which are installed into the subsurface soil using vibrational techniques. Prior to testing, a drilling company is contracted to perform deep soil mixing at the designated site. A vibration tool is used to install each 10-inch diameter steel casing to 40 feet below land surface. Steel casing is now ready to be filled with a gravel-iron mixture. A concrete mixing truck combines a blend of iron and gravel. The gravel-iron mix can arrive on site pre-measured and ready for placement in the casing. When filled to a level 1 foot above the groundwater table, a sulfuric acid rinse is introduced inside with the bottom plug still intact, so that the solution remains inside the casing for 12 hours. When the acid rinse is introduced, it has a pH of approximately 2. Once in contact with the oxidized iron filings, the pH shifts to 5. When the pH reaches 5, the plug is removed from the bottom of the casing, allowing the sulfuric acid to drain. The casing is then extracted from the subsurface using the vibration tool. To begin the deep soil mixing operation, a 4-foot diameter rig is mobilized to the site. An auger mounted on a guided set of rails is lowered 40 feet into the ground. It functions much like a cake mixer, blending the columns of zero-valent metal with the native soil.
Although permeable reactive barriers are by far the most common way to apply iron metal in the remediation of environmental contaminants, there are other methods that have potential. This panel presents some of the alternatives to PRBs. Commercialization of iron-permeable reactive barriers followed soon after the process had been demonstrated at the Borden Field site. A few years later, design and installation of iron PRBs had become an important part of the business of groundwater remediation. A few of the key players in this business helped out with production of this CD-ROM, and they are mentioned here. Here's a summary of the major points presented in Chapter 2. Move the mouse over the blue rectangles of text for elaboration on each point and its relation to other points made in the chapter. Chapter 3 provides the chemistry background necessary to understand the iron wall technology. Only by mastering this material can scientists and engineers hope to improve and to expand the applicability of this technology. This page provides an outline of the contents of Chapter 3. The topics progress from mechanisms to energetics and finally to kinetics of the reactions that occur in iron-permeable reactive barriers. If you want to skip a particular topic, just click on the appropriate blue oval. These molecules represent chemicals from the major classes of groundwater contaminants that are treatable with the iron wall technology. Clicking on any of the 2D molecular structures will bring up a 3D structure of the contaminant. Click on the 3D image and move the mouse to rotate the image so you can view the molecule from all sides. The 3D image will enlarge when you press the Shift key and shrink when you press the Control key. Dechlorination is one of the most important contamination degradation reactions, and this reaction accounts for most of the beneficial effects of iron when used to treat contaminated groundwater. The primary mechanisms by which dechlorination can occur are illustrated by these two animations. Reductive dehalogenation, also known as hydrogenolysis, results in cleavage of a carbon-chlorine bond and formation of a new carbon-hydrogen bond. The mechanism is shown here as a sequence of elementary reaction steps. First, an electron transfer, then loss of chlorine, then addition of a second electron, then protonation. Reductive elimination is shown here as a concerted one-step process, where carbon-chlorine bonds on adjacent carbons are broken, and a new carbon-carbon double bond is formed. D represents the electron donor, such as iron, which initiates the elimination process. An oxidation-reduction reaction, or redox reaction, involves a transfer of electrons from one molecule to another. Start the animation to see the reduction of iron 3 by iron 2. This is a very simple reaction where there is no net chemical change. The next panel shows examples of more complex redox reactions in which there is a net chemical change resulting in new reaction product. This is a representation of electron transfer from an iron 2 ion to an iron 3 ion. Note the change in size of the ions as the electron is transferred. Two examples of redox reactions are shown in this video. The movie shows the reaction of iron and zinc when added to a solution of copper sulfate. These are redox reactions because electrons from the metals are transferred to the dissolved copper ions. Iron is added to the copper sulfate solution in the vial on the left, and zinc is added to the copper sulfate solution in the vial on the right. The middle vial serves as a control. When the metals are added, the copper sulfate solution gradually turns clear, as copper 2 ions are transformed to copper metal which plates out on the iron and zinc. The bubbles that appear in the vial to which zinc was added are hydrogen gas, which is from the reduction of water by zinc. The vial to which iron was added never becomes as clear as the one to which zinc was added because the iron is ultimately oxidized to iron 3, which is rust-colored in aqueous solutions. A balanced chemical equation conserves both atoms and charge. One must work with balanced equations to understand how much of each compound will be consumed or produced, and to understand the reaction mechanism. Click on the Balance Equation buttons to see the step-by-step procedures used to balance redox reactions. This equation represents the first step in the rusting of iron, the reaction of iron with oxygen to produce ferrous ions. This equation represents the second step in the rusting of iron, the reaction of ferrous ions with oxygen to produce rust. This equation represents the reduction of carbon tetrachloride by iron, which is a contaminant degradation reaction that occurs in an iron wall. The rules for assigning oxidation states are not so easily applied to organic compounds as they are for inorganic compounds. Oxidation states for the central carbon atoms, however, can be assigned by considering the electronegativities of the atoms in the bonds. This figure shows the reduction of HCA to either PCE or PCA, and illustrates how the oxidation state for the central carbon atoms can be assigned based on the bonds. The oxidation state for each bond is in blue, and for each carbon atom is in pink. Electrochemical cells provide a way to isolate redox half reactions. The flow of electrons that is required to sustain the reaction occurs through a wire that connects the two half reactions. This configuration makes it possible for the redox reaction to do electric work. Start the animation to see, in molecular detail, an electrochemical cell based on the iron-copper redox reaction seen in a previous panel. The right half of the electrochemical cell is made up of a copper electrode in a solution of cupric sulfate. Blue spheres represent the cupric ions. The left half of the electrochemical cell is made up of an iron nail electrode in a solution of ferrous sulfate. Green spheres represent the ferrous ions. As we saw in an earlier video, iron reduces cupric ions. In the electrochemical cell, the electrons from the iron, illustrated as white spheres moving through the connecting wire, travel to the copper electrode where they reduce the cupric ions to copper. The net result is an increase in the number of ferrous ions and a decrease in the number of cupric ions. To prevent charge buildup, which would shut down the electrochemical cell, a salt bridge must be used. Cations from the salt, shown as red spheres, migrate to the copper cell to balance the loss of cupric ions, and the chloride ions, shown as yellow spheres, migrate to the iron cell to balance the increase in ferrous ions. Cell potentials are used to determine if a redox reaction will be spontaneous. Cell potentials are calculated using the Nernst equation, which is shown above. Mouse over the equation to learn more about the parts of the equation and how they are evaluated. In this panel, we illustrate the calculation of cell potentials for two reactions that were seen in other parts of this chapter: the reduction of cupric ions by zinc and the rusting of iron by oxygen. Click on the reaction thumbnails to see how to apply the Nernst equation to each case. The reduction of a contaminant by iron metal must be a spontaneous reaction if it is to be useful in groundwater remediation with iron-permeable reactive barriers. Spontaneous processes are those that result in an increase in the amount of disorder in the universe. Calculating the net change in disorder for the universe can be difficult for some reactions. However, this criteria can be restated in terms of the cell potential. For a redox reaction to be spontaneous, the cell potential must be greater than 0. The energy of a system changes as a reaction proceeds from the reactants to products. These changes can be illustrated in a reaction coordinate diagram, like the one shown in the lower left corner. Click on the labels in the diagram to learn more about what these diagrams represent. As an example of a redox reaction, we've used the corrosion and rusting of iron several times in this chapter. While we normally try to inhibit the corrosion of iron to minimize damage to iron structures, there are some beneficial uses for this reaction. The iron-permeable reactive barrier is probably the most important example. Another interesting example is the use of corrosion to generate heat in small hand warmers that are used by skiers, sports fans, and others. This panel shows a reaction coordinate diagram for the second step in the degradation of carbon tetrachloride by iron, the breaking of the carbon-chlorine bond after the electron transfer. Start the animation to see this correspondence between the position on the reaction coordinate diagram and the bond dissociation. You can view the reaction using one of three models: ball and stick, molecular orbital, or electron density. The simulation was generated using the molecular modeling software called CACHE. To describe the rate of a chemical reaction, a rate law must be determined. The rate of most degradation reactions is proportional to the contaminant concentration. This is a characteristic of first-order reactions. Click on the equations shown in the left panel to learn how to predict how the contaminant and product concentrations will change with time during the degradation. To determine the rate constants necessary to evaluate a rate law, controlled experiments in the laboratory are usually necessary. The graph shows how this is usually done. The data are plotted so that the slope will be the negative of the rate constant, assuming the degradation reaction follows first-order kinetics. Rate constants for reduction of contaminants with iron metal will be used in Chapter 4 to determine how much iron is necessary for an iron wall. For a summary of the major points presented in Chapter 3, move the mouse over the blue rectangles. You can also use this panel as a kind of self-test by anticipating what the text will say when you mouse over each summary item. This is the fourth and final chapter of the MERL CD-ROM. It explores some state-of-the-art scientific issues regarding the design and operation of iron walls. The discussion also illustrates the application of key chemical concepts that were presented in the previous chapters. The outline for Chapter 4 includes the topics shown here. Move the mouse over each oval for elaboration on each topic. Click on an oval to jump to that topic, or click on the right arrow to start Chapter 4 at the beginning. To fully appreciate the material on design calculations that follows, it is important to begin by considering some of the basic chemical processes that influence the performance of iron-permeable reactive barriers. Most of these issues revolve around the complex chemistry of the iron-water interface. In most cases, engineering design calculations for iron-permeable reactive barriers have been done in terms of half-lives determined from a feasibility study. This approach is reasonable, but has limited flexibility. The approach is illustrated with data from an early field site. A more powerful and scientifically rigorous way of doing basic design calculations is presented here. This analytical approach is based on a simple kinetic model like those presented in Chapter 3. To apply the analytical design method, it is necessary to have rate constants for degradation of each contaminant. Representative values of these rate constants are summarized in this figure. Move the mouse over each orange dot for details on each compound. Both the conventional and the analytical methods of doing design calculations are highly simplified. To incorporate the effect of transport in the design process, it is necessary to use a reactive transport model. An interactive version of such a model can be accessed by clicking on the button that launches the external software package called Igor. The Igor model provides a customized interface that allows you to vary the parameters using the controls provided. The graph will then update automatically. For more explanation, click the Help button from within the Igor application. Another modeling challenge is to incorporate the effect of simultaneous and parallel reaction pathways on the concentration of contaminants and their degradation products. An interactive version of such a model can be accessed by clicking on the button. In addition to the primary design considerations just discussed, there are a host of secondary considerations that may need to be considered. 5 of the most important are summarized here. Up until now, in our discussion of kinetics and the design of iron walls, we have treated the iron surface as if it did not change with time. However, the corrosion of iron leads to the precipitation of iron oxides. The diagram shown here illustrates how these processes are related and how they are affected by the redox potential and pH. Such representations are known as EHPH or Pourboire diagrams. As indicated by the EHPH diagram for the iron-water system, precipitates on iron metal will be ubiquitous under environmental conditions. These precipitates that are formed on the iron wall will be complex in composition and structure. Some of what is known about these precipitates is shown here. As precipitates accumulate in a permeable reactive barrier containing iron metal, the effects of these precipitates are likely to become very important. Not very much is known about these effects yet, but their significance is an area of active research. Some effects that are likely to be most important are summarized here. As iron walls become increasingly common, interest is shifting to the questions: how long will they last, and what can be done when they begin to fail? In time, complete answers to these questions should emerge, but for now, we can only provide examples of what developments can be expected in the near future. These frames are the last materials that are implemented in the current version of the MERL CD-ROM. This page summarizes the major points presented in Chapter 4, as well as some important links to material presented in other chapters.